सजेशन देना चाहता हूँ।
Oh, so where are we? So we are studying this, right? Atoms and molecules. So now continue the study. Where I get stuck? Start the timer. We study for 12:40. Timer. Hey timer. It's here. Now, what is law on conservation means law of definite proportion? Try again. So questions I'll be first. I see the videos once again. Conservation law.
Have a look at this reaction. This is wood burning and forming ash. Now, if I ask you to take mass of this wood that is burning and take mass of the ash that is formed,
Okay,
which mass will be more?
don't
Well,
know.
if you're like me, you will say that the mass of the reactants or the wood over here is
Okay.
more than the mass of the ash formed, right? Ash can even fly off in the air, it's so light. It seems that burning or combustion destroys matter. Or we can say that when something burns, mass decreases. That is, the mass of the reactant, the piece of wood here, will be more than these ashes. But what if I say that the mass really remains the same? How can that be? Let's find out. Well, we'll talk about the law of conservation of mass in this video, which basically states that mass can neither be created nor destroyed in a chemical reaction. For example, if we take magnesium and heat it so that it starts burning, which will look kind of like this. Look at how it burns with a really bright flame. Now the reaction involved here is magnesium plus oxygen, which forms magnesium oxide, and it also releases light and heat energy. We can represent this reaction in the form of atoms. So let's say we have two atoms of magnesium. They will react with one molecule of oxygen, which already has two atoms of oxygen, and then it forms two compounds of magnesium oxide. Now you can see that no atoms were created or destroyed in this reaction. We can extend this to say that no mass is created or destroyed. So if we say 48 grams of magnesium and 32 grams of oxygen, then we will get 80 grams of magnesium oxide. Or if we take, let's say if we take 20 grams of magnesium and 10 grams of oxygen, then we will get 30 grams of magnesium oxide. No mass is created or destroyed in a chemical reaction. Now let's come back to the wood example. Over here, wood reacts with oxygen to form carbon dioxide, water vapor, and some ash. If this reaction happens in the open, the gases formed will float in the air. But if we had a sealed container like this, where we can entrap or contain the gases. Then, if we measure the mass of the reactants, that is wood and oxygen, and if we measure the mass of the products, that is carbon dioxide, water vapor, and ash, they will come out to be the same. So, if there is, let's say, 500 grams of wood and oxygen combined, then we will get 500 grams of combined carbon dioxide, water vapor, and ash. Similarly, if we carry out the reaction of magnesium with oxygen in a sealed container, we will get the products of the same mass as that of reactants. So this is the law of conservation of mass, which says that mass can neither be created nor destroyed in any chemical reaction. Let's talk about law of definite proportions, or it's sometimes called law of constant proportions. Now this law states that in any chemical substance, the elements are always present in definite proportions by mass. Now instead of proportions, we can call them ratio to make the definition simpler. So we can say that the elements are always present in definite or constant ratio by mass. Let's try to understand this with the example of water. So we know that water is H2O, and if we apply this rule to water, it says that water as a compound is always formed from the same ratio of hydrogen and oxygen. And specifically, we can see that water is formed from two atoms of hydrogen. So this is two atoms of hydrogen and one atom of oxygen. So this will always be the ratio of hydrogen to oxygen atoms in any sample of water. It doesn't matter if it is tap water or water in an ocean or a lake,
Or
the
a
ratio of
hard water.
hydrogen and oxygen atoms in that sample of water will be 2:1. Now this rule also extends to mass. So we know that every atom has a mass of its own, and we know that one atom of hydrogen weighs 1 atomic mass unit. So that will be two atoms will be 2 atomic mass units. So let me write 2 AMU. One atom of oxygen has an atomic mass of 16 AMU. So that will be 16 AMU, 16 atomic mass units. And now from here I can say that the mass ratio of oxygen to hydrogen will be 16 is to 2, and this can be simplified to 8 is to 1. This is a ratio of oxygen to hydrogen by mass. And what this really means is that in any sample of water, either a drop or water in a glass or water in an ocean, doesn't matter if you take 50 liters, 10,000 liters, or even just 1 ml of water, the mass of oxygen present in that sample will be 8 times the mass of hydrogen that is present in that sample. And this is the law of definite proportions. It holds true for every other chemical substance, even for carbon dioxide. So you see carbon dioxide or water in an ocean, doesn't matter if you take 50 liters, 10,000 liters, or even just 1 ml of water, the mass of oxygen present in that sample will be 8 times the mass of hydrogen that is present in that sample. And this is the law of definite proportions. It holds true for every other chemical substance, even for carbon dioxide. So you see carbon dioxide being formed when organic matter burns. You also exhale carbon dioxide. And doesn't matter how much carbon dioxide you take, the ratio of oxygen to carbon atoms or the mass of oxygen to carbon will always be the same in any sample of carbon dioxide.
Okay, so this is that. Now we're going to do the some calculations or some questions. Kilogram of certain metal burns oxygen to give 10 gram of its oxide. How much metal should be heated in steam to give 12 gram of oxide? So what it said? It said that 2 gram what? It says that 2 gram of certain metal burns in oxygen to give 10 gram of its oxide. 2 gram of certain metal burns in oxygen to give 10 gram of its oxide. How much metal should be heated to steam to give 12 gram oxide? 2 gram certain metal burns in oxygen to give 10 gram. So first 2 gram gives 10 gram. So 1 gram will give 10. That's what said, right? 2 gram gives 10 gram. Say 2 gram of certain metal burns in oxygen to give 10 gram of its oxide. 2 gram, if we burn 2 gram, then we get 10 gram. So 1 gram, then 2 gram, and now says 12 gram oxide. What needs to be done? So 12 gram, for 12 gram oxide, how much you have to burn? So 10 gram by 2 gram. Let's destroy the gram into 12. Now 2 6 12. Now 6 10 are 16. So we need 60. We need 60 or what? 60. No, that's the wrong answer. Why? It's it's not only 60. It says 2 grams certain metal burns in oxygen to give 10 grams of oxide. How much metal should be heated in steam to give 12 gram oxide? So for 12 gram oxide, how much? I think it will be not 2. It will be 2.5 or half something. So how can we calculate it? So if we need to calculate it right, so first we need to do is that first we need to for this first we need to for this we have to I think I have to use chat gpt for that. Chat gpt I have to know the rule how to do it. So if I paste here, it will give me answers, not answers, the rule how to do. So metal plus stream equal to metal oxide plus hydrogen. We all know general reaction metal plus stream. If you do metal plus stream, then you get metal oxide plus hydrogen. So now they are saying method to solve. So step 1, write balanced equation. So it will be balanced equation if you do the equation type like Fe3 Fe plus 4H2 Fe3 O2 OH2. So use molar masses. So Fe we don't need that of a much. We only need this. If 2 gram oxide needs only metal, then metal required 230 gram metal divided by 232 into 12. Why? Because then for 12 oxide, right? Similarly here to do what question says that 2 gram of certain metal bonds into oxygen to give 10 grams oxide. How much metal should be heated in steam to give 12 gram oxide? 2 gram of certain metal burns in oxygen to give 10 gram of its oxide. How much metal should be heated in steam to give 12 gram oxide? So now 2 gram of certain metal burns in oxygen to give 10 gram of its oxide, right? So how much metal should be heated in steam to give 12 gram oxide? So first 2 gram. First 2 gram. So they are saying 2 gram. Here is what it say. Like metal required 168 gram metal hydroxide needs. So 2 gram divided by 2 gram divided by 2 gram 2 gram divided by 10 into need how much? 12. Need 12, then 2 fives are now 5 5 twos are 10, 2 2 5 2 now point 0 fours are 20 2.4. So answer will be 2.4, I guess. Check it out. Yeah, that's the answer. Because according to the law of constant proportion, the ratio of masses, the metal and oxygen remain constant in the metal oxide respective of its source. So here it's saying, here you can see that they are saying that according to the law of constant proportion. Constant proportion means what will be remain here also remain here. So the ratio of masses of the metal and oxygen remain constant in a metal oxide respective of its source, right? So here is saying that metal divided by oxygen 1 equals to metal divided by oxygen 2. This is 1 and this is 2. So 1 2 divided by 10 minus 2. Why 10 minus 2? 10 minus 2 because this is why 10 minus 2? 2 by 10 minus 2 and here equal to m by 12 minus m. So 0.25 where do we get 0.25? 0.25 into 12 minus m equal to m. So here it's very complicated. So now what you can do this simple. If you don't understand any of the questions, you can simple copy and paste in ChatGPT and say ChatGPT explain me easy way, then it will explain you easy way that you can get it. So now it's doing. So find ratio of given data. So oxygen is always same. Ratio of metal oxygen always same. So from first oxide, metal equal to 2 gram and oxygen equal to 8 gram. Why 8 gram? Metal equal to 2 gram and oxygen equal to 8 gram. So ratio, why 8 gram? Find the ratio of given data. So now I don't understand the why 2 gram? Because it's saying 8 gram. So I am asking another question here. I'll copy paste it and ask why. Why you do that? Now you tell. Good question. This is a key question. So why we do? Oxygen equal to 10 minus 2. Because the total mass of oxide 10 gram. Out of this metal is 2 gram. So it's saying 2 gram of certain metal burns in oxygen to give 10 gram of its oxide. So 2 gram, 2 gram. So 2 gram. If we burn 2 gram of certain metal burns, then it will give us 10 gram of its oxide. So it gives a 10 gram of oxide. In that oxide, there are 2 gram metal present, right? Two burns or something burns metal present in that 2 gram. That present in 10 gram. So that's why decreasing, or we can say it, subtracting 2 from 10 gram, then we get 8 gram. You get it now? Why we do that? We are doing because in that, if 2 gram metal, now oxygen, metal, we burning oxygen, burning in oxygen, and we're getting 10 gram of oxide, 10 gram of oxide, we're getting 10 gram of oxide. So in this 10 gram of oxide, there are remaining metal is present, 2 gram metal is present. That's why we are minusing 10 gram to 2 gram, so getting 8 gram. This 8 gram is our oxygen, bro. Here, this 8 gram is our oxygen. So metal, now we're doing metal is to oxygen ratio, then 2 gram is to 8 gram, that will be 1 is to 4, right? 1 is to 4. So meaning 1 gram metal reacts with 4 gram oxygen. So here it's saying 1 gram metal reacts with 4 gram oxygen. So it's saying, sorry, so it's saying that, right? Oxygen. So now step 2, apply to new oxide 12 gram total. Step 2, apply to new oxide 12 gram total. Apply to new oxide 12 gram. So let me assume m gram metal, and then oxygen is 12 gram minus m gram, right? So now using the ratio, same ratio, so m divided by 12 minus m equal to 1 by 4. So we are doing this right away. So it's the first thing that given. Now next, now next is now next now next now next is what? Now next is that, next is what? Now next is given, only given oxygen, oh sorry, oxide is 12 gram given. So here we don't know metal, how much metal is used here. Metal m, we're assuming m, and oxygen also, oxygen is 12 minus m. So now we're using this, so m divided by 12 minus m equals to previous one 1 by 4. So now if we calculate it, equal to and calculate it like cross multiplication, then we get 4m minus 12 minus m. Now m 5m equals to 12. Now we can get m equal to 12 divided by 5. So what we will get? We will get 2.4 approx. 2.4. We will get 2.4. So 2.4 we will getting. So 2.4 is the answer here. See, 2.4 gram. So that's how he do it. Now if I now Now if I ask GPT to solve this a quick method, then see how you will answer. You'll answer same way, just the same. So direct formula is metal equal to metal part by total part into total mass, like this. Metal direct direct formula is metal part by total part to total mass. So how the final ratio is given 2 gram, 10 gram, 8 gram. We can order 1:4. So add parts 1:4, add 5 parts, 1 plus 4, 5 parts. Direct formula is metal equal to metal part by total part. So metal part is 1. How? Why 1? Metal part of 1. How? Metal part is 1 because 1:4, right? Metal part is 1 and total part is 5 into 12 total mass. So this is the, so if you want to do a simple way, like instant way, quick way, then you can do parts. So use this formula. What is the formula? Metal equal to metal part divided by total part into what? Into total mass. Total mass into total mass. So you can use this formula to do easiest and quick way. So if question given, this question, like this question given, if it's given 2 gram of certain metal bonds in oxygen to give 10 gram of oxide, and how much metal should be given. So now you will do easily that 2 gram metal given and oxygen is 10 minus 2 equals to 8. Now we do 8 is to 2 or 2 is to 2 is to 8. We will get 1 is to 4. Now add them up. Add 1 plus 4 equal to get 5. Now use the formula. What's the metal part? Metal part is here 1. Metal part 1 and total part is 5 into how? Total what? Total oxide or total, what's saying, total 12 gram oxide, total metal, total mass. Okay, total mass. Oxide total mass, total mass is 10, sorry 12. So 5, 12 beta 5 equal to 2.4. This is the simplest and quick way. Gram, this is the answer. Now we will use second question. What is second question says? Second question says that from the following postulates, give me 1 second. There is noise coming, and there is no very noise coming, so I'll shut the door for you. So wait a second. Let's continue. So this is the formula. Second question, it says from the following postulates. The second question it says from the following postulates of Dalton's atomic theory, identify the one that is result of the law of conservation of mass. So from the following postulates of Dalton's atomic theory, identify the one that is a result of the law of conservation of mass. So choose one. Law of conservation of mass. So choose one. Question already said that, so following the postulates of Dalton's atomic theory, identify that is result of law of conservation of mass. So they are asking to identify in the options, choose one whose whose results are shown like law of conservation of mass. So we will first read the options, then we will answer it. So first, atoms combine ratio of small whole numbers to form compounds. I don't think so. This will be our answer. All matter is made of very tiny particles called atoms. It's true, but here it says Dalton's atom theory identify the one that is result of law of conservation of mass. Atoms are invisible particles which cannot be created nor be destroyed in a chemical reaction. Atoms of a given element are identical in mass and properties. So what is the right answer in this? So I think according to my what I understand that law of conservation mass or delta atom theory, the C will be the answer. Let's check it out. Yes, C is the answer. Because why? Because the law of conservation of mass states that mass can neither be created nor, this is the main theme line for conservation mass. What? Ki law neither be created, mass neither be created or nor be destroyed. So that's why I choose this. Atoms are invisible particles which cannot be created or nor be destroyed in chemical reaction. That's why. Now there is another question here. So calculate the amount of Na2CO3 formed when 11.2 gram Na2O completely reacts with 8.8 gram CO2. Completely reacts light. So calculate the amount of Na2CO3 formed when 11.2 gram Na2O completely reacts with 8.8 gram CO2. So it's saying calculate Calculate the amount of Na2CO3 formed when 11.2 gram Na2O completely reacts with 8.8 gram of CO2. So now we'll do the calculation. So what it's saying, calculate the amount of Na2CO3 formed when Na2O completely reacts with CO2. So it's saying that Na2, sorry, I'll first remove it. It's saying Na2O3, sorry, Na2O, so why, damn bro, damn. So it's saying Na2O, right? It's saying right. Na2O completely reacts with 8.8 grams of CO2 plus CO2 equals to what is giving us. It is giving us Na2O3, Na2O2 and O3 plus, oh, sorry for that. So it's saying that, right, ki like this. So it are giving a complete reaction to 8.8 gram of CO2. Na2CO3 plus something will remove, right? C, where is the CO? Na2O3, CO3, sorry, I did the wrong. Na2CO3, it will be C here, CO3. They are giving us Na2CO3 formed. So now we have to calculate out that, calculate the amount of Na2CO3 formed, amount of, so it's simple basically. 11.2 gram plus, if we do, it's saying that it given 11.2 gram Na2 and CO2 8.8 gram. So simple, if we both if we add them both, then we can get that number. We can get this number. Which number? We can get this number. How its total mass? So it will be 20 gram. So answer will be 20. See, now third question. What mass of carbon is needed to completely react with 4 gram oxygen to form CO2? What mass of carbon is needed to completely react with 4 gram oxygen? You are getting it. It's saying what mass of carbon is needed to completely react with 4 gram oxygen to form CO2. So what mass of carbon is needed to completely react with 4 gram oxygen to form CO2? So now we are doing here. What mass of carbon is needed to complete react with 4 gram oxygen to from CO2? Okay, so CO2, right, and 4 gram oxygen given. So CO2, if we calculate CO2, then we get, here we get, if we CO2, CO2, if we what the atomic masses we are getting here. So for C we are getting 12 plus for O2 we are getting 32. How much you are getting? 44. So CO2 44, right? So what mass of carbon is needed to complete react with 4 gram oxygen? Complete react with 4 gram oxygen. So first let me analyze the question. What mass of carbon is needed to complete react with 4? So for 2 gram, for 32 gram oxygen, it's need 12 gram carbon, and for 4 gram, how much you need for 4 gram oxygen? It's a question, bro. For 32 for 32 gram, we need 12 gram carbon dioxide for O2. When it's saying for 4 gram oxygen, how much we carbon needed for 4 gram? So 32 divided by 4, 4 total. First part divided total part into 4 gram. How much? 4 4 11. So 32 11. So 3 are 30. No 3 are no 3 are 11 2s are 22. 11 2s are 22. 2 to 0 1 10. Point showing 0. 11 9s are 99. 1. So it will go like this. So if we add one more 0, it will 10. It will give us 10. Then we have to add a 0. So let me 2.90. Answer will be same or not? 2.9. I don't think so. Answer no. 2.9 is so we will see the steps. So steps are given as so 32 gram O2 combined with 3 gram, then do 44 grams CO2, right? So oh, it will doing this. 1 gram oxygen combines with 1 gram 1 gram 12 32 gram 1 gram oxygen O2 12 32 gram C, then 4 gram into 4. Oh, it's that simple. They are using this rule for 1 gram for 1 gram. Sorry, look, wait. 1 gram O2 we are using 12 by 32, right? 12 means carbon and 32. So 4 gram O2, how much you will use? 12 by 32 into 4. 4 8 the 2 6 the 2 4 the 2 2 the 2 3 the. So 3 by 2 1.5, I guess. Yeah, 1.5. So 1.5 is the answer here. Check it. Yes. So 1.5 is the answer there. Now we're going to elements and atoms. Now let's see.
For thousands of years, humans have observed different substances in their environment.
Yes.
And these different substances tend to have different properties.
Okay.
Not only do they have different properties, these might reflect light, differently have a distinct color, or even
Okay.
exist as a solid, liquid, or gas at a given temperature.
Okay.
But we also observe how they react with each other in certain circumstances. And here are pictures of these substances. This right here is carbon, and this you see is in its graphite form. This right here you see is lead. And this you see here is gold. All the
Okay.
substances shown here, sourced from this website, are in their solid form.
Okay.
So, we also know that there are different types of air and air particles, each with unique properties and behaviors under varying conditions. Depending on the type of air particles, such as carbon, oxygen, or nitrogen, they each exhibit different physical and chemical properties. There are substances that exist as liquids, and if you raise the temperature high enough, even solids like gold or lead can become liquid. Similarly, burning carbon can transform it into a gaseous state, releasing it into the atmosphere and breaking its molecular structure. So these are
Okay.
things that humanity has observed for thousands of years. But it leads to a natural question that used to be a philosophical question, but now we can answer it a little bit better. And that question is, if you keep breaking down this carbon into smaller and smaller chunks, is there some smallest chunk, some tiniest possible unit of this stuff, of this particular fundamental substance that still has the properties of carbon in it? And if you broke it down further, you would eventually lose the properties of carbon. And the answer is yes, there is. And in order to get our terminology right, we call these distinct pure substances with specific properties at certain temperatures and chemical reactions, fundamental elements of matter that make up everything in the known universe.
Okay.
Here, carbon, lead, and gold are all elements found in nature. You might think that water is an element, and historically, it has been referred to as one. But now we know that water is made up of more basic elements. We
Okay.
know it's made of oxygen and hydrogen atoms bonded together, and all of our known elements are
Okay.
systematically listed here in the periodic table of
Periodic table
elements.
is elements.
C
Yeah.
stands for carbon.
Yeah.
Here I am covering the elements most relevant to humanity, and over time, you will likely learn them all. It's oxygen. This is nitrogen.
Yeah.
This is silicon. This one is gold, written
Gold.
as AU.
AU.
This is lead. And you
Lead
see,
PB.
the most basic unit of any of these elements is the atom, the fundamental building block of all matter in the known physical universe. So if you were to keep digging in and keep taking smaller and smaller chunks of this, you would finally get to a carbon atom. Do the same here, and you'll reach a gold atom. You do the same thing here, and you'd get a tiny particle, for lack of a better word, called a lead atom. And you wouldn't be able to break that down anymore and still call that lead for it to still have the properties of lead. And just to give you an idea about something I always struggle to imagine, is that atoms are unbelievably, unimaginably small in nature. For example, carbon, my hair is also made of carbon. In fact, most of me is made out of carbon. And in fact, most of all living things on Earth are made out of carbon.
Okay.
And if you took a strand of my hair, which is
Yeah.
mostly carbon made, you'd see its structure. If you took my hair, it's black, not yellow, but yellow contrasts better. If it were black, you couldn't see it on screen. But if you were to take my hair here and I asked, how many carbon atoms wide is it? If you took a cross section, not the length, but the width, how many carbon atoms would possibly fit across it? You might guess, as you have been told that they're very small, so maybe there are 1,000 carbon atoms there, or 10,000 or 100,000. I would say, no, there can be 1 million carbon atoms or even more at times. Or
Okay.
even you could string 1 million carbon atoms or more across the width of the average human hair. This is obviously an approximation, but now that gives you a sense of how small atoms are. Pluck a hair from your head and imagine lining up a million tiny objects across its width.
Okay.
Not its length, but its width. The width of a hair is hard to see, yet a million carbon atoms could fit across it. It's remarkable that we know there is a fundamental building block of carbon, the most basic unit of any element, forming the essential structure of everything we see, touch, and interact with daily, shaping the world around us. But what's even more impressive is that those basic building blocks are related to each other, and a carbon atom is made up of even more fundamental particles. A gold atom is made up of even more fundamental particles, and they're defined by the arrangement of those fundamental particles. If you change the number of fundamental particles, you could alter an element's properties, reactivity, and stability, or even transform it entirely. Just to understand it a little bit better, let us now talk about those fundamental building blocks. So you have the proton here, which
Okay.
actually defines the element. The number of protons present in an atom's nucleus determines its identity and chemical behavior.
Okay.
We will talk about nucleus too. But this is what defines an element, determining its unique properties and interactions. If you look here, the periodic table is arranged by atomic number,
Yeah.
and the atomic number is literally just the number of protons in the element.
Okay.
So by definition, we know that hydrogen has one proton.
Hmm.
Helium, you see, has two protons. Carbon here has six protons.
Yeah.
Carbon can't have seven protons. If it did, it would be nitrogen and would not be carbon anymore. And oxygen has eight. If you added another proton, it wouldn't be oxygen anymore. It would be fluorine. So it defines the element, determining its unique identity. The atomic number, which represents the number of protons, is the number written at the top of each element in the
Okay.
periodic table. The number of protons is always equal to the atomic number, defining the element's identity and distinguishing it from all others. They put that number up here because it's the defining characteristic of an element. The other two constituents of an atom, I guess we could call it that way, are the electron and the neutron,
Neutron,
both
yes.
essential to atomic structure and fundamental to chemical interactions. The
Okay.
model you build in your head will become more abstract as we explore chemistry. A way to visualize it is with protons and neutrons at the atom center, forming the nucleus, while electrons orbit, governing chemical reactions and atomic behavior. They're the nucleus of the atom. For example, carbon has six protons.
Okay.
Here we have 1, 2, 3, 4, 5, 6 number of protons. Carbon 12, which is a version of carbon, will also have 6 neutrons. Carbon can have versions with different numbers of neutrons. Neutrons and electrons can change, but the element will be the same. But the protons can't change as it creates a different element. So let me draw a carbon 12 nucleus here. So 1, 2, 3, 4, 5, 6 number of neutrons here. This right here is the nucleus of carbon 12, and sometimes it will be written like this, and sometimes they'll actually write the number of protons as well for clarity.
Okay.
The reason we write it as carbon 12 after counting 6 neutrons is that this represents the total number of protons and neutrons in its
Neutrons.
nucleus.
Okay.
One way to view it, though we'll refine this understanding later, is that it reflects the sum of these fundamental particles here. This carbon here, by definition, has an atomic number of 6, but
Yeah.
we can rewrite it here to remind ourselves. At the center of a carbon atom is its nucleus, and carbon 12 has 6 protons and 6 neutrons. Another version is carbon 14, which still has 6 protons here but 8 neutrons, so the neutron number can change. But
Okay.
this is carbon 12 right over here. And if carbon 12 is neutral, and I will give a little nuance on this word in a second as well, it'll also have 6 electrons. Now, let us draw these 6 electrons here, so they will be 1 to 6 electrons here. One way, perhaps the first order way, to think about the relationship between electrons and the nucleus is to imagine electrons buzzing around it in constant dynamic motion. One model here is you could kind of think of them as orbiting around the nucleus, but that's not quite right. They don't orbit like a planet orbits the sun, but it's a good conceptual starting point. Another way to think about it is that electrons jump or buzz around the nucleus. Reality becomes very strange at this scale, and truly understanding electron behavior requires quantum physics. But a first mental model in your head is that at the center of this carbon 12 atom, you have this dense nucleus right over there containing protons and neutrons. These electrons here are jumping around this nucleus. The reason electrons don't just drift away from the nucleus and remain bound as part of the atom is that protons have a positive charge, while electrons have a negative charge. These charges are fundamental properties of these particles, creating the electromagnetic force that holds atoms together and governs chemical interactions and bonding. So when do you consider what a charge is beyond just a label? One thing we know about electromagnetic force is that unlike charges attract each other. So the best way to think about it is that protons and electrons, each of them having different charges, attract each other, while neutrons are neutral. So they're really just sitting here inside of the nucleus.
Okay.
And they do affect the properties on some level of some of these for some atoms of certain elements. But the reason why we have the electrons not just flying off on their own is because they are attracted. They are attracted toward the nucleus and move at an unbelievably high velocity, constantly in motion. It's hard to grasp, and we touch on a strange part of physics when discussing what an electron is actually doing in its quantum state. But
Okay.
it moves rapidly, jumping around enough that it doesn't simply fall into the nucleus, which you see is one way to think about it in quantum mechanics.
Mm.
And so, as I mentioned, carbon 12 right over here, defined by its number of protons. Oxygen is defined by having 8 protons. But once again, electrons can interact with other electrons or they can be taken away by other atoms. And that
Mm.
actually forms a lot of our understanding of chemistry. It depends on the number of electrons an atom or element has, how those electrons are configured, and how the electrons of other atoms, whether of the same or different elements,
Mm.
are arranged. This allows us to predict how an atom of one element might react with another atom of the same or a different element, whether it will bond, repel, or be attracted to it, influencing chemical reactions, molecular structures,
Mm.
and the properties of matter. For example, another atom can sometimes steal an electron from a carbon atom, altering its charge, stability, and reactivity, and we will explore this more in the future. Just because, for whatever reason, and we will discuss this later, certain neutral atoms of some elements have greater electron affinity, influencing chemical interactions. If one of those swipes an electron from carbon, it'll have fewer electrons than protons, resulting in a positive charge. So then it would have 5 electrons and 6 protons here, and then it would have a net positive charge. In this carbon 12 atom, the first version here had 6 protons and 6 electrons, properly cancelling the charges. So
Okay.
losing an electron leaves 5, thus
Mm.
creating a net positive charge. We will explore this more throughout the chemistry playlist, but hopefully you appreciate how fascinating and cool this is getting.
Yeah.
We can already reach this incredibly fundamental building block of matter called the atom.
Yeah.
What's even more fascinating here is that this fundamental building block consists of even more fundamental components,
Mm.
which can be rearranged to alter an atom's properties or even transform it into an atom of a different element.
Okay. Elements and atoms. So now we got a theory. Now we have to read it. So introduction, they give an introduction here. So what is your body made of? So my body, what is my body made of? You first thought might be that it is made up of different organs such as your heart, lungs, and stomach that work together to keep your body going. Or you might zoom in a level, say that your body is made up of many different types of cells. However, at the most basic level, your body and in fact all of life as well as non-living world is made of atoms, often organized into larger structures called molecules. So so atoms and molecules follow the rules of chemistry and physics even when they are part of a complex living breathing being. If you learn in chemistry that some atoms tend to gain or lose electrons or from bonds with each other, those facts remain true even when the atoms or molecules are part of a living thing. In fact, simple interactions between atoms played out many times and in many different combinations in a single cell or a larger organisms, so are what make life possible. So one could argue that everything you are, including your consciousness, is that byproduct of chemical and electrical interactions between a very large number of non-living atoms. So as an incredibly complex being made up of roughly incredibly complex being made up of roughly roughly of this number of atoms. How many zeros are there? 7, 3, 3, 6, 3, 9, 3, 12, 3, 15, 3, 18, 3, 21, 3, 24, 3, 27 atoms. 7 and 27 zero atoms. You will probably want to know some basic chemistry as you begin to explore the world of biology and the world in general. So matter and elements. So the term matter refers to anything that occupies space. Matter terms defines anything that occupies space and has a mass. Anything that occupies space and has a mass, we call it a matter. In other words, the stuff that the universe is made of of made of all matter is made up of substances called elements, which have specific chemical and physical properties and cannot be broken down into the other substance through ordinary chemical reactions. So gold, for instance, is an element, and so is carbon. There are 118 elements, but only 92 occur naturally. The remaining elements have only been made in laboratories and are unstable. So in our periodic table, 118 elements are there, but only 92 are naturally occurred, and others are man-made or chemically made, lab-made. We can call it a lab-made, man-made. So each element is designed by its chemical symbol, which is a single capital letter, or when the first letter is already taken by another element. So a combination of two letters. Some elements follow the English term of the element, such as C for carbon and Ca for calcium. Other elements' chemical symbols come from their Latin names. For example, symbol for sodium is Na, which is a short form of natrium, the Latin word for sodium. So the Latin word for sodium, the four elements common to all living organisms, the four elements common to all living organisms are oxygen, carbon, hydrogen and nitrogen, which together make up about 96% of the human body. In the non-living world, elements are found in different properties, and some elements common to living organisms are relatively rare on Earth as whole. All elements and the chemical reaction between them obey the same chemical and physical laws regardless of whether they are a part of living or non-living world. So the structure of an atom. So structure of atom, what it says. So it's saying an atom is the smallest unit of matter that retains all of the chemical properties of an element. Yes. For example, a gold coin is simply a very large number of gold atoms molded into the shape of a coin with small amounts of other contaminating elements. Gold atoms cannot be broken down into anything smaller while still retaining the properties of gold. So a gold atom gets its properties from the tiny subatomic particles it's made up of. So an atom consists of two regions. The first is the tiny atomic nucleus, which is in the center of the atom and contains positively charged particles called protons and neutrals. Uncharged particles called neutrons. So the second, much larger region of the atom is a cloud of electrons, negatively charged particles that orbit around the nucleus. The attraction between the positively charged protons and negatively charged electrons holds the atom together. So most atoms contain all three of these types of subatomic particles, protons. So electrons and neutrons. So hydrogen H is an exception because it is typically has one proton and one electron, but no neutrons. So the number of protons in the nucleus determines which element an atom is, while the number of electrons surrounding the nucleus determines which kind of reactions the atom will undergo. So the three types of subatomic particles are illustrated below. For an atom of helium, which by definition contains two protons, like this. So this is called atom structure. Now you can see in that atom structure there are two protons there present and two neutrons. Always remember, in an atom there is, in the center of it there is a proton and neutron. Always remember, if there is a one proton then there is a one neutron always. If there is a two proton then there is a two neutron always. But electrons are not in center, they are in the outer shell, and they are in the outer shell of the neutron proton, and they are the, like, you can assume they will circle around the electrons. So now protons and neutrons do not have the same charge, but they do have approximately same mass. But they do have same mass. It's not same charge, but they do have same mass, proton and electrons. So 1.67 into 10 to the minus 24 grams. Since grams are not a very convenient unit for measuring masses that tiny scientists choose to define an alternative measure. The Dalton atomic mass unit AMU. So atomic mass unit we call in short form AMU. A single neutron or proton has a weight very close to 1 AMU. Electrons are much smaller in mass than protons, only about 1 divided by 118 18,000 of an atomic mass unit. So they do not contribute much to an element's overall atomic mass. On the other hand, electrons do greatly affect an atom's charge. So as each electron has a negative charge equal to the positive charge of a proton in uncharged neutral atoms, the number of electrons orbiting the nucleus is equal to the number of protons inside the nucleus. So the positive and negative charges cancel out, leading to an atom with no net charge. So here saying proton and neutrons and electrons are very small, and most of the volume in an atom greater than 99% actual. With all this empty space, you might ask why so-called solid objects don't just pass through one another. The answer is that a negatively charged electron clouds of the atoms will repel each other if they get too close together, resulting in our perception of solidity. So these are the things. So here is a question, and even there are several forces. Says there are 180 elements, but only 92 occur naturally. The remaining elements have been many laboratories and are unstable. Why are the elements many laboratories is unstable? So they're saying there are several forces at work inside a nuclei of atoms. The electromagnetic force of the protons wants to push them away from each other. Fusion allows these protons to get close enough together for the stronger yet shorter ranged. So nuclear force to overpower the electromagnetic force. So neutrons will help add to this number force, but they tend to become unstable when they get into too great of concentration, and the weak force will cause them to decay into problems. Protons decay into problems. With all of that to consider, as you get as you get larger and larger nuclei with more protons, the electromagnetic forces increases, as well as the distance in the nuclei, putting more strain on the nuclear forces holding it all together. The ratio of neutrons to protons gradually increases to try to compensate, but this results in the neutron getting more unstable themselves, resulting in more opportunity for weak forces to destabilize them. Hence, larger atoms become more unstable. So there are believed to be certain numbers ratio that are inherently more stable. These are called magic numbers. It's thought that another one of these magic numbers lies just beyond the range of currently known elements, which means we could potentially discover some new elements that are relatively stable and extremely massive. So it's saying too much things in this paragraph. So now let's go to the next video, introduction of atom.
In most topics, you must advance before addressing the philosophically interesting aspects. But
Yeah.
in chemistry, it just starts right from the get go with what's arguably the most philosophically interesting part of the whole topic, and that's the atom. The idea of an atom was conceived by philosophers long ago, and you could look it up on the different philosophers who first philosophized about it. They said, hey, if I start with an apple and keep cutting it, eventually I will reach something that can't be divided further. Let me draw a nice apple so it doesn't look like a heart. There you
Okay.
go. I have a nice apple. And you just kept cutting it into smaller pieces. So eventually you get a piece so small, so tiny, that you cannot cut it anymore. I am
Okay.
sure some philosophers went out with a knife and tried it, thinking, if I could just get my knife sharper, I could cut it again. It was a completely philosophical construct, which, frankly, isn't too different from how the atom is today. It is really just a mental abstraction that allows us to describe a lot of observations we see in the universe. But anyway, these philosophers said that at some point there would be a tiny part of the apple they wouldn't be able to divide anymore. They called that an atom, and it doesn't have to just be for an apple. They said this is true for any substance or any element that you encounter in the universe. The word atom is Greek for uncuttable or indivisible, a concept that lasted until we learned more about the nature of matter. Now we know that it is cuttable, and even though it is not a trivial thing, it is
Okay.
not the smallest form of matter. We now know that an atom is made up of other, more fundamental particles like protons, neutrons, and electrons. Let me write them. So we have the neutron, and I will draw in a second how they all fit together in the structure of an atom. We have a neutron, we do have a proton, and we have electrons. These particles play crucial roles in the properties of atoms, and understanding how they interact is key to understanding the behavior of matter. And you might already be familiar with this. If you look at the old videos about atomic projects, you will see a drawing that looks something like this. Let me see if I can draw one. So you'll have something like that, and you will have these things spinning around looking like this. They have orbits that look like that,
Yeah, orbits.
and maybe something like
They
that.
are electrons.
The general idea behind this kind of nuclear drawing, and I am sure they still show up at some government defense labs or something like that, is that there is a nucleus at the center of an atom. You have a nucleus at the center of an atom. And we know that a nucleus has neutrons and protons. We will talk a little bit more about which elements have how many neutrons and how many protons. Then, orbiting. I will use the word orbit for now, although we will learn in a bit that orbit is actually the incorrect or even mentally misleading way of visualizing what an electron is doing. But the old idea was that you have these electrons that are orbiting around the nucleus, very similar to the way the Earth orbits the Sun or the Moon orbits the Earth. It has been shown that this is the very wrong way to think about it. When we
Okay.
cover quantum mechanics, we will learn why this model does not work and what contradictions arise there.
Okay.
When you try to model an electron like a planet orbiting the sun. But this was the original idea of viewing an atom, which we will explore later as we dive deeper into atomic structure. I think this is the most mainstream idea. Now, I said an atom is philosophically interesting. Why is it philosophically interesting? Let's study it. Because what we now view as the accepted way of viewing an atom really starts to blur the line between our physical reality and the idea that everything in the world is just information, which is fascinating to consider. There really isn't any such thing as true matter or true particles in the way we define them in our everyday life. You know what? For me, a particle is like a grain of sand. I can pick it up. A wave could be like a sound wave or a change in energy over time. But we'll learn, especially in quantum mechanics, that it all gets jumbled up as we approach the scale or size of an atom. But anyway, I said this was an incorrect way of doing it.
Okay.
What's the correct way then? So it turns out that this is not really a picture, but a depiction. So it's an interesting question, what I just said. How can you have a picture of an atom? Because it turns out that most wavelengths of light, especially the visible ones, are much larger than the size of an atom. So it is not something you can observe in the same way, it's by reflected light. But suddenly, when you are dealing with an atom, reflective light can almost be seen as too big or too blunt an instrument to properly observe it.
Okay.
Anyway, this is a detailed depiction of a helium atom. A helium atom has two protons and two neutrons,
Neutrons in
or at
center.
least this particular helium atom has exactly two protons and two neutrons. And
Oh.
they depict it here in the nucleus right there. Maybe these are the two. I am assuming they're using red for proton and purple for neutron. The neutron in purple color seems like more of a neutral and subtle color, and they're sitting calmly and firmly at the very center of this atom. And this whole haze around, those are the two electrons that helium has, or at least this atom has. Maybe it could gain or lose an electron, but these are electrons. You say, hey Sal, that does not make, how can two electrons be this blur that is kind of smeared around this atom? And that's where it gets philosophically interesting. So you cannot accurately describe an electron's path around a nucleus with the kind of traditional orbit idea that we've encountered when we look at planets, or if we just, imagine things at
Hmm.
kind of a much larger and broader scale. It turns out that an electron, you cannot precisely know exactly its momentum and exact location at any given point in time due to quantum uncertainty. All you can know is a probability distribution on where it is likely to be. And the way they depicted this, black is a higher probability, so you're much more likely to find the electron here than you are here. But the electron could be anywhere, even here, though it's completely white there, but with a very, very low probability. And so this function of where an electron is located in space at any given moment, this
Yeah.
is called an orbital, not to be confused with a traditional circular or elliptical orbit.
Hmm.
Remember, an orbit was something like this. It's like the, Venus going around the sun.
Okay.
So it's very physically easy for us to imagine. While orbital is actually a mathematical probability function that tells us where we are likely to find an electron. We will cover more of that in quantum mechanics, but it's beyond the scope of this introductory chemistry lecture series. But it's really interesting, right? An electron, its behavior is so bizarre at that scale that you cannot, to call it a particle is almost misleading. It is called a particle, but it's not a particle in the sense that we are used to in our everyday life. It's this thing that you cannot even say exactly where it is. It can
Yeah.
be anywhere in this haze, and we will learn later that there are different shapes of the hazes as we add more and more electrons to an atom. To me,
Okay.
it starts to address kind of philosophical issues of what matter even is, or do the things we look at, how real they are, or how real they seem, at least as we've defined reality. Anyway, I don't want to get too philosophical on you, but the whole notion of electrons, protons, they're all kind of predicated on this notion of charge. And we've talked about it before when we learned about Coulomb's law. You could review Coulomb's law videos in the physics playlist for understanding. The basic idea is that an electron has a negative charge, a proton, sometimes written like that, has a positive charge,
Hmm.
and a neutron has no charge in
No
any
charges.
situation.
Yeah.
And so that's what was tempting about the original electron model, is
Hmm.
that they say, okay, if this thing has positive charges, right, because let's say this is two neutrons and two protons, and for example, it's the helium atom, then we will have some positive attraction charges here. We
Yeah.
have some negative charges out here. Opposite charges naturally tend to attract. And so, if these things had some velocity, enough velocity and proper direction,
Hmm.
they would continuously orbit around this central core, just the
Oh.
way a planet will orbit steadily and predictably around the sun in space. But now we learn that even though this is partially true, the
Hmm.
further an electron is from the nucleus, the greater its potential energy is. Since it naturally tends to move toward the nucleus due to electrostatic attraction, which plays a crucial role in atomic structure and influences chemical reactions and bonding behavior significantly. But because of all of the mechanics, it won't just do something simple like move in a path like that, like a comet would do around the sun. It actually has this kind of wave like behavior where it just has this probability function that describes it. But the further away an orbit is, it does have more potential. And we will explore that in future videos. But
Okay.
how do you recognize what an element is. I have discussed the philosophy and all of that. How can I determine if this is helium? Is it based on the number of neutrons or the number of protons?
Number
Is
of
it by the
protons.
number of electrons? Well, the answer is by the number of protons.
Protons,
So
yeah.
if you know the number of protons in an element, you know exactly what that element is. The number of protons is called the atomic number.
Yeah.
The atomic number is a unique identifier for each element in the periodic table and determines its chemical properties. Now, let's say I said something has 4 protons. How do we know what it is? The number of protons in an atom determines its element. Well, if we have not memorized it, we can look it up on the periodic table of elements, which we will be using a lot in this playlist. You will say, oh, 4 protons, that is beryllium. And the atomic number is the number you see up there,
Yes,
and that's the number of protons. And that is the single most, that is what differentiates one atom from another.
yeah.
If you have 15 protons, you are
Potassium.
dealing with phosphorus.
Oh, sorry,
Now,
phosphorus.
all of a sudden, if you have 7, let's say you have 7 protons, you
Neon.
are dealing with nitrogen. If you have
Sorry,
8,
nitrogen.
you are dealing
Neon
with
is
oxygen.
10.
That is what defines the element.
Okay.
Now, we will talk in the future about what happens with charge and what happens when you gain or lose electrons. But that does not change the element you're dealing with. And likewise, changing the number of neutrons doesn't change the element you are dealing with, but it can create isotopes.
Yeah.
But that leads to an obvious question of, well, how many neutrons and electrons do you have? Well, if an atom is charged neutral, that means it has the same number of electrons as protons, balancing out the overall charge of the atom. And so, let's say that I have a carbon atom and its atomic number is 6 and its mass number is 12. This means it has 6 protons and 6 electrons, and the mass number tells us the total number of protons and neutrons in the nucleus. Now, what does this mean? So, let me say further that this is a neutral particle. This is a neutral atom. So, the atomic number for carbon is 6, meaning it has 6 protons. That tells us exactly how many protons it has. So if I were to draw a little model here, and this is in no way an accurate model, I would draw 6 protons in the center, and the weight of these protons, each proton is 1 atomic mass unit. We'll talk more about that, how it relates to kilograms. It's a very small fraction of a kilogram, roughly 1.6 times 10 to the minus 27th of a kilogram. This is the mass of a single proton or neutron. So let's say each of these is 1 atomic mass unit, and that's approximately equal to, I think, 1.67 times 10 to the minus 27 kilograms. This is the mass of a single proton or neutron.
What the?
This is a very small number,
1.67
unimaginably tiny in scale. It's
Yeah.
almost impossible to visualize, at
Yeah.
least it is for me. This tells me the mass of this particular carbon atom, and this can actually change from one carbon atom to another. Essentially, this is the mass of all the protons plus all the neutrons in the atom. It's almost impossible to visualize, at least it is for me. This tells me the mass of the entire carbon atom, this particular carbon atom, and this can actually change slightly from carbon atom to carbon atom depending on the number of neutrons. This is essentially the mass of all of the protons plus all of the neutrons combined together. So in this case, we have 6 protons, so we must also have 6 neutrons in addition to the 6 protons, making the total mass of the atom. Now, where are the electrons? Well, do you remember? I said it's neutral. So the proton has an equal positive charge as the electron's negative charge. So this is a neutral atom and it has 6 protons, so it also has 6 electrons. Let me draw that for you. So we said it has 6 neutrons in here. 1, 2, 3, 4, 5, 6, and 6 protons.
6 protons.
So that's the nucleus with electrons surrounding it. And then if we were to draw the electrons, well, I could draw it in a smear, but if we want to kind of visualize a little better, we could say, okay, there's going to be 6 electrons orbiting it. 1, 2, 3, 4, 5, 6.
5, 6.
And they're going to be moving around in this unpredictable way that we would have to describe with the probability function. And the interesting thing about it is most of the mass of an atom is sitting right in here. I mean, you might notice that when people care about the mass of a proton, when they care about kind of the atomic mass number of an atom, they ignore the electrons. And that's because the mass of a proton, one proton mass-wise, is equal to 1,836 electrons, and making the electrons practically insignificant. So, For thinking about the mass of an atom, for basic purposes, you can ignore the mass of an electron.
Okay.
It's really the mass of the nucleus that counts as the atom's mass, since the protons and neutrons contribute the vast majority of the atom's mass overall. Now, you might see this periodic table here, and you say, okay, they gave us the atomic number up there, right? The atomic number of oxygen is 8.
8.
It means it has 8 protons.
Hmm.
The atomic number of silicon is 14. It means it has 14 protons. Now, what is this right here? Let's see. Let's look closely in carbon. They have this 12.0107, which is the atomic mass or atomic weight of carbon. So let me write this right there. Atomic weight of carbon. And the atomic weight of carbon is 12.0107. This value accounts for the natural isotopic abundance of carbon, which includes both carbon-12 and a small amount of carbon-13 found in nature. Now, what does that mean? Does that mean that carbon has 6 protons and then the remaining 6.0107 neutrons, ultimately making up its atomic mass precisely? It has kind of this fraction of a neutron? No. It means that if you were to average all the carbon, all of the different versions of carbon you find on the planet, and average the number of neutrons based on the quantity of the different types of carbon, this is the average you would get. So it turns out that carbon, the two major forms, and the main one you will commonly find is carbon-12. So that's like this. So that has 6 protons and 6 neutrons in its nucleus. And then there's another isotope of carbon. Now, an isotope is the same element with a different number of neutrons. Another isotope of carbon is carbon-14, which is much more scarce on the planet. We don't know how much in the universe, but on the planet. Now, if you were to average these, not just a simple average, you would get carbon-13 with an atomic weight of 13. But you weight this one more as it exists in larger quantities on Earth. This is nearly all the carbon you see, but there's a bit of this. So if you weight them appropriately, the average becomes this. So most of the carbon you will find, and if you weight them appropriately, the average, but there's a bit of this. So if you weight them appropriately, the average becomes this. So most of the carbon you will find, and if you just found carbon in some place naturally occurring on Earth, on average, its weight in atomic mass units is going to be approximately 12.0107. But that idea of an isotope is an interesting one. Remember, when you change the neutrons, you're not changing the actual fundamental element. You're just getting a different isotope, a different version of the element. So these two versions of carbon are both isotopes. Now, I want to leave this video, which I think is kind of the neatest idea behind atoms, and it's kind of the most philosophically interesting things about them, is that the relative size. So we have these electrons, which represent very little of the mass of an atom. I mean, it's 1,000th of the mass of an atom are in the electrons. Even them. It's hard to even describe them as particles because you cannot even tell me exactly where and how fast one of these particles is moving. They just have a probability function, so most of the atom is sitting inside the nucleus. And this is interesting. If you look at an atom on average, if you say, this is my atom, and let's say I have two atoms that are bonded to each other, and I were to say, how much of this is actual stuff? And when I say stuff, that's an abstract concept, because the nucleus holds all the mass and density. It turns out that it's actually an infinitesimally small fraction of the volume of the atom, where the volume of the atom, it's hard to define because the electron can pretty much be anywhere. But if you view the volume as where you're most likely to find the electron, or with 90% probability you're likely to find the electron, then the nucleus is, in a lot of cases. But it is 1/10,000th of the total atomic volume, making it extremely dense and compact compared to the surrounding space. So if you think about it, when you look at something, if you look at your hand, or if you look at the wall, or if you look at your computer, 99.99% of it is free space. It is nothing but it is vacuum. If you had ultra small, I guess we could call them particles, most of them would pass straight through whatever you look at. So it already starts to kind of question our holds on reality and perception. And this is a proven fact. This isn't just theory right here. That if you take anything down to the building blocks, down to the atomic level, most of the space of that kind of quote unquote object is free vacuum space. you could go straight through it if you could get down to that scale. I mean, this image of a helium atom, they say right here, this is 1 femtometer. A femtometer is 1 quadrillionth of a meter. That means the nucleus of an atom is incredibly small compared to the size of the atom. This is the
Okay.
scale of the nucleus of a helium atom, right? 1 femtometer. This
One
is 1 angstrom,
femtometer.
right? And they say that equals 100,000 femtometers. Just to get a sense of scale, 1
Mhm.
angstrom is 1 times 10 to the negative 10th meters. So the atom is roughly on the scale of an angstrom. In the case of helium, the nucleus is even a smaller fraction. It's 100,000th. So let's say you had liquid helium, which must be very cold. If you look at it, most of it is free space. If you're looking at an iron bar, the great majority of it is free space. And we're not even talking about maybe
Mhm.
there's some free space inside the nucleus that we could talk about in the future. But to me, that just blows my mind that most things we look at are not really solid. They're really just empty space, but they
Empty
look solid
space. Solid.
because of the way light reflects on them or the
Yeah.
forces that repel us. But there really isn't kind of something to touch there, that most of this right here is all free space. I think I have said the word free space now, and I think I will leave further mind blowing to the next video.
Okay. So in the ions molecules we will study in the next live stream. So today we wrap up the live stream the study. So this is we'll today learn about law of conservation, law of concentration, about atoms. We all learned that today. So next in the next stream we'll complete this chapter, I guess. Yeah. Let's see how many are remaining. Oh, in the next stream we'll complete the chapter. That's all. So let's end the stream. So bye. Bye and good afternoon. Bye. Bye. Yeah, bye.